on your sheet, what you're going to write down here, there's my pen, okay, is the first one you're going to see is going to be about a catalyst. Okay, so the first one you're going to see is what does a catalyst do for our rate of reaction. And remember, our rate of reaction is either we're going to speed up or slow down. Okay, and so we're going to draw what we have to start with. So you've got a flask. Okay, you have your Erlenmeyer flask. Do your best to draw it. I'm not very good, so you don't have to do it beautifully. Okay, and then we're going to draw that we've got just a liquid in here. I'm going to draw it blue because it's easier, but we've got some hydrogen peroxide in there. Okay, and that's all that's in there. Okay, and what it's doing is it's slowly releasing water and oxygen gas. Okay, so the balance equation for the decomposition of hydrogen peroxide is 2 moles of hydrogen peroxide will decompose into 2 moles of water. This is actually going to be, and I'm going to put in here that this is a gas plus oxygen gas. Okay, so we're going to get a mixture of 2 gases. We're going to get some liquid, but we're going to get a mixture of 2 gases. What I'm going to add in is a catalyst. So I'm going to put it, usually when we write our catalyst on here, we're going to write it in here. It is going to take place in the reaction for a minute, but remember we learned yesterday, it does take place, but then it goes back to what it was, right? And we're going to use manganese dioxide, and this is my catalyst. Okay. So as we're sitting here, we see that this is not doing much at all. It is decomposing. If you came and really looked at it, it does have some little bits of bubbles on here, okay? But you can't really tell. So what I'm going to do is I'm going to add a catalyst and speed that up. You're going to see stuff come out of this, okay? It's going to be, don't worry about it, it's just oxygen and water vapor, okay? All right. And then we'll talk about what it's doing and how it speeded it up. All right. Now, this stuff I'm going to show you guys is black, okay? So when we put our manganese dioxide in here, it's just like a black powder. So remember, 2 things a catalyst has to do. Number 1, speed up the reaction, right? Number 2, it must be the same at the end of the reaction as it was at the beginning, which means I need it to go back to being black. Okay? All right. So now you can see, what did that do for the reaction of the decomposition? Did it speed it up or slow it down? Speed it up. Okay? Now what we can see is this is just all water vapor and oxygen. I'm not too worried about it. But if you look, number 1, it's very hot. So if it feels hot, is it endothermic or exothermic? Exothermic. And also you can see at the bottom, can you guys see down there? What color is down there? Black. So did our manganese dioxide go back to what it was? Yes. So that's why manganese dioxide is classified as a catalyst. Okay? Because not only did it speed it up, but it also went back to what it was, okay? What it was at the beginning. So our explanation here, we're going to write our explanation. First, we're going to write our reaction graph. Of course, I have black powder everywhere now, okay? Is our reaction graph, when we talk about a catalyst, anyone remember what a catalyst does to the activation energy from yesterday? It lowers it. So that's all it did. So remember, we have a graph, and this graph is going to be energy graphed to time. Okay? And we're going to draw 2 lines into this graph. The one that before I added a catalyst and then after. Okay? So the first one I'm going to do okay? You pick a color. I'm going to start it off here. Remember, these are my reactants. I'm just going to put an R for reactants, okay? And what happens is it goes up the hill, right? Up the hill over the activation energy. It's exothermic. So is energy going in or out? If it's exothermic, out. So that means, did my energy increase or decrease? Decrease, so it's got to be lower. So I'm going to go down, it's got to be lower. The products will be lower in energy than my reactants. Does that make sense? Yeah? Okay. And remember, we're also going to label this. I'm going to label this from where my reactants start to where they end. This is my original activation energy. Okay. And I'm going to label this line just down here. I'm going to say this color is no catalyst. Okay. So that's how much reaction energy or activation energy I need without a catalyst. But when I added my manganese dioxide, we're still starting at the same energy. Maybe I should do something. Let's do, how about red? That'll be nice and easy to see. Red, then what happens is it lowers that activation energy. So it still goes up the same, but then it's a lower hill, okay? And it reaches the end time, of course, you can also see is shorter because of that rate of reaction is increased, okay? It's faster, less time. So then we're going to do this one. This one is with a catalyst, okay? And if I was to mark that activation energy, I'm going to do it in red. Then it's from where the reactants are to that top of the hill, okay? So this is the activation energy here. Remember that activation energy, okay, is just the energy needed to get up and over that hill to head to products, okay? So a catalyst takes that activation energy and drops it. You don't need as much. Because remember, you want to remember the three things you need for a reaction to happen. What are the three things? First thing, you need the molecules to what? What do you need them to do? Collide. They're already colliding, okay? The second thing is they need to collide with what? With sufficient energy, kinetic energy. Remember that? We talked about kinetic energy was the speed of the particle. So they have to collide with each other with enough energy to get it to work. And the third thing, you might remember the third thing? What's that third thing that they need? The right orientation, hit on the right side. They're moving fast enough, of course, then we can get them there. This activation energy is that energy hill. They have to have enough energy when they collide to get that reaction to happen. So what the catalyst did was it lowered that energy needed. So now more of them can make it over the hill. Does that make sense? Yes? See your faces. More of them can make it over that activation hill and head to products, okay? So let's explain that. So manganese oxide is a catalyst because it did the two things, right? One, increased reaction rate, and two was the same at the end of the reaction as it was in the beginning. Okay. So manganese oxide lowered the activation energy needed to get the reaction started. which helped more collisions to happen with sufficient energy. Okay? Okay. So, a catalyst does not increase the collisions, but it lowers that energy so more of them can make it over the hill. Okay? More of them have enough energy to get over the hill. And as you can see, if you look at now look at the flask, you can see it's much more black. The whole thing has stopped. There's some, you can see the black powder is still at the bottom. Okay? So it's what it was. Okay? Questions on catalysts? All right, the next thing we're going to do is we're going to see concentration happen. Okay? I'm going to have two little bowls underneath this camera in just a minute. One bowl will have a 5 molar, or sorry, I keep thinking 5 because I was making 5 for something else. 12 molar. Hydrochloric acid. The other bowl will have a 1 molar hydrochloric acid. Okay. Inside these bowls, we will have a little strip. I'll tell you what that is in just a second. This is going to be magnesium. Okay? And the reaction that's going to happen is we're going to have 2 moles of hydrochloric acid plus 1 mole of magnesium is going to react to make magnesium chloride and hydrogen gas. Okay? So, some of the things you're going to see that it's working is you'll see gas bubbles. Okay? And we're going to see which one's going to happen faster. Is it going to be the one with the 12 molar? Remember, it's 12 molar. That's 12 moles per 1 liter, okay, of hydrochloric acid. And this is a 1 molar. That's 1 mole in 1 liter, okay? So which one has the higher concentration, 12 or 1? Which is a higher concentration? 12, okay? So that means we have more moles over here, okay? All right, bring those up. All right, so I have them labeled. There we go. Now it's adjusted. So I'm going to put a 12 molar solution in here and a 1 molar solution in there. So you can kind of see some bubbles happening, right? Can you guys all see the bubbles happening? Which one is happening faster? Which one? The 12. Okay, remember we talked about, I hate this, yeah, it stinks. Okay? Hydrogen gas smells. Okay? So, what do you see? What happened to the strip here? It's gone. That one's still going. So, we know that this one had a higher rate, right? Okay? We got to think about why. What are those? Remember, they have to have, right? They have to have collisions. Okay? Put that back there. Okay? It stinks. Okay. So when we have more molecules in there, like if I put more people in here, are we going to have more collisions between you guys or less collisions? More collisions. So when we put more concentration or more moles, we have more atoms, right? Which means they're going to collide more or less? More, okay? So when we do this one, we're going to label this that this went faster. This was slower. Okay. How do we know we're going to draw in our hydrogen bubbles so we can see? So this one had a ton of bubbles, right? Lots of bubbles, lots of hydrogen. Gas. Well, this one just kind of did a little bit. And actually, it's still not done, right? So you can see how fast that reaction, the 12 molar one, went really slow, okay? So the explanation for this one is the concentration, or what we call here in chemistry molarity, of hydrochloric acid is higher in the 12 molar, which increases the number, I'm just going to shorten number of this, of molecules in the same volume. This increases collisions, which will increase the rate of reaction. Okay. So if we want, sorry, I put reaction, that's just out of my brain. I do it RXN is a short way to write reaction. You guys can write it out if you want. I just noticed I just did that. Okay? It's just my shorthand when I write notes. Okay? So, reaction. Oops. Okay? So, if we want something to speed up, we can add more of it. Okay? If we add more of it, we're going to speed up that reaction. That means we have more molecules to collide, and that rate of reaction is going to go faster. Okay? Questions on concentration? Okay. All right. Stop smoking. Good. Finally. It smells bad. All right. The next one I'm going to set up is going to be fun. It's glow sticks. Has anyone ever played... This one's hot, so I'm going to put this one up there. Okay. All right. Does anyone still need this one up? Okay. So I'm going to have 3 different, temperatures of water. So I'm going to put some ice in this one, so I have really cold. This is just room temperature. This one's hot. Okay. There is a reaction within a glow stick. It's a little bit complicated. Okay. Grab my So a glow stick has a lot of stuff in it. Okay. It's a very complicated equation, but I don't want you guys to focus on it too much. But we're going to write it just so you guys know. You don't have to memorize this. Okay. All right. So we're going to see what temperature does. Okay. And we're going to have our 3 beakers. So we're going to have cold. We're going to have warm. And we're going to have hot. Okay. The balance equation for a glow stick, okay, is 2 moles of C6H3 Cl3O2. This is why you don't want to eat it or put it in your mouth, because it has chlorine in it. Okay. It also has hydrogen peroxide in it. Okay. Not things we want to eat. Okay. And when you break it, this is what starts the equation. So then we get here H3Cl3OH plus heat in the form of light, and it also makes carbon dioxide, okay? Within the plastic, okay? And we're going to place glow sticks in each spot, and we're going to see what happens, okay? Okay, so I'm going to break a bunch of them. I'm going to add some ice to this one so we get it nice and cold. I'm going to turn off the lights and we're going to play with our glow sticks. Hopefully they're all working. That's the plastic. Okay. A few more. Okay, so let's watch what these guys do. So as you guys are watching these, kind of a dud, okay? As you guys are watching these, we can look and see what happens to the brightness. The brighter it is, okay, the more reaction we have. Does that make sense? The brighter it is. Because remember, we're producing light and heat. As you guys are watching these, what do you guys say? Which one is the which ones are the brightest right now? Which ones? Right. Because remember, we're increasing the temperature, right? So probably better ones. Oh yeah, these are nice. Okay. And as you can see, which ones are the lowest? Cold. Now, do you think we can reverse this process? How do you think I can make the cold ones brighter? What should I do? Let's try it. Okay, so the hot ones you guys are saying are the brightest. So let's take the hot ones and switch them out. See if we can reverse what we did. Okay? So what do you see happening to the ones in the cold? Are they getting dark? Are they getting brighter or lighter? Lighter. And what's happening to the ones that were in the cold? Here, they're getting what? Brighter, right? Because the brighter we are, if you can see how they're getting a little bit brighter than where they were? And you can see these guys have started to dull out, right? Let's try this. Let's take some of these. I'm going to switch this way. The ones that are just working, okay? And you can play with these and put them back and forth. Because remember, when you're looking at this reaction, the heat and light is a product, right? So I can force it to make a lot of product or a little bit of product, okay? So if we think about this, which one has a higher rate of reaction? Cold, warm, or hot? Good. Which one has a low rate of reaction? Cold, okay? So temperature, we can drive it however we want, right? Please don't throw things in my room. We can put them, make them hot, and make that reaction happen faster, like when you're cooking a pancake, right? Or we can make it cold and slow that reaction down. Why do you guys think you put your food in the refrigerator? Why do your parents yell at you if you leave food out? Because it spoils. When you put it in the refrigerator, that is a chemical reaction. When you put it in the refrigerator, what happens to that reaction of spoiling? Slows it down. Okay? So temperature does a lot. Okay? All right, so let's write out, okay, what we need to on our paper. Okay? All right, so we had our hot and our cold. Okay? And you can use whatever color you like to make your little, you know, your wonderful glow sticks, okay? So we're going to put one in the cold. I'm going to use orange. I'm going to put one in the warm and one in the hot. And we're going to show, turn this on so we can see again, the brightness. So, to show the brightness, what you can do here on the paper is just kind of do some little things that make it look like it's bright. But for this one, make it really, really bright, okay? And we're going to write down here, this was the slow reaction, okay? Because it was very dim. This was the fast reaction because it was very bright, okay? Okay. Put those back there. All right, so let's go ahead and explain that. Okay. So for temperature, remember we talked about yesterday, it has two different things, okay? As temperature increases, the kinetic energy, and what was kinetic energy? We reminded ourselves yesterday, what is it? Kinetic energy is what? Amelia, what was it? You said it. Speed. Good. That's our speed. Okay. Of particles, okay? Or molecules, okay? Increases. If something's going faster in the same amount of volume, are we going to have more collisions or less collisions? More collisions. This increases the number of collisions. It also increases the energy of those collisions. Remember they talked about yesterday that when you have two cars and they're going faster, you're going to hit with a more energy, right? All that energy is then transferred to other type of energy. So when two molecules have a higher energy, they're going to hit more and transfer more of that energy to that heat and light, which comes out of this reaction. That's why we get brighter. So we're not only increasing collisions, but we're also increasing the energy of those collisions. More going over that hill, okay? These both increase the rate of reaction. Okay? Question on temperature. Okay. Just find a seat. Okay? Thank you. Okay? Questions on temperature? Okay. All right, the last one I'm going to do is one you guys did not learn about yesterday. It's not in the video. There's one more way we can increase the rate of reaction. And this one is about surface area. When I say the surface area of something, what does that mean? Does anyone know what surface area is? What is surface area? Well, it's kind of like a volume, yeah? Like how big the surface is, yes. So it's like when you guys are, remember we talked about with solubility, right? If you had a big rock of sodium chloride or salt, and then you had some crushed up salt, which one is going to dissolve faster? The crushed up, because it has a higher surface area. It can interact with that solvent more, okay? The same thing here, okay? If you give those molecules a bigger space where they can interact with other things, you're going to have a faster reaction. We're going to see how this works, okay? All right, so I'm going to do two things here. The first thing I'm going to do is I'm going to have a beaker, okay? Just a small beaker, okay? And I'm going to place inside it some alcohol, just isopropyl alcohol, like what your parents clean your wounds with. You know that stuff sometimes they put on your wound and it really stings, hurts like heck. Hopefully they haven't done it. My mom used to do it all the time, okay? It disinfects things. So I'm just going to add some alcohol, and then I'm going to add fire to it. So that's my energy I'm adding to it. And we're going to see what it looks like in a small beaker. Okay. Then we're going to place it into a 5-gallon bottle. And we're going to do the same thing. And I'm going to put in here, I'm just going to kind of put a color in here that I'm going to put alcohol. It's going to be at the bottom here. But you're going to see I'm going to actually spread the alcohol out around my larger bottle. And we're going to see what happens to that rate of reaction, okay? This is a combustion reaction, okay? So alcohol is C2H3OH. Plus, remember that combustion reaction has to have oxygen with it. That's in our air. It's going to react to make carbon dioxide and water. But it's also going to make heat and light. Okay? So we're going to see what happens when we take the same substance, but instead of keeping it in the bottom there, we're going to spread it out all over a large area. Okay? All right. Okay. So we have, I'm going to have to back this up so they can see it. Okay. Is we're going to have a little bit in here. Okay. I'm going to turn off the light. All right, we're going to add a little bit of alcohol. I'm going to take this off so it's a little darker. Okay, I'm going to add a little bit of alcohol here. Just a little bit. I'm not going to put a ton of it in there. Okay. And I'm just going to add some energy to it. Okay. So you can see this is a pretty controlled burn, right? It's just happening slowly. Not going to set anything on fire here, okay? I'm going to go ahead. We can put it out, okay? By just getting rid of that. Yes. Oh, recycling. Christian, can you grab that recycling? Take it over there. Thank you. Okay. So that first one was just a nice controlled burn, right? Was it very fast? No, kind of slow, kind of easy going, right? So on your sheet, what you're going to do here is, let's say, okay, we kind of just are going to draw in what we saw. So it was just kind of like a little fire. And we're going to see what's going to happen to that rate of reaction when I spread it out into the 5-gallon bucket. Okay? So let's take a look. So now what we're going to do is we're going to take a little bit of alcohol. I'm going to pour it in there. What's in there is just rock salt. Okay, guys? It's just rock salt. It's just so that I can get that. It'll absorb into the rock salt a little bit. And then when I shake it, it spreads. And then we're going to do the same thing. And then what we're going to do is we're going to go ahead. Let's see what we can do here. What was that, faster or slower? Faster. So when I spread it out, okay? When I spread it out, that rate of reaction happened faster. So we're going to draw. Let's draw that into our paper, okay? And you guys heard the sound, right? That's why they call it the whoosh bottle, because it makes that sound. So you had a lot of, right, come out, right? And we're going to label this as slow reaction, fast reaction, okay? Please don't do this at home. Don't go play with your parents' 5-gallon water bottles, okay? It can be quite dangerous if you don't know what you're doing. Unfortunately, the teacher at West, when I was there, blew a bottle up. So, please don't do it because they put too much in it, okay? So, it is not, it looks safe when I do it because I know how much to put in there. Okay, so please do not go home and try this. Okay, all right. That is my warning to make your parents happy in case I get an email. Okay, if you don't, yeah, the bottle blew up, shattered, cut him, a student, and went through and damaged the roof. It was not good. Okay, so please do not do it if you don't know what you're doing. Okay, all right. When we increase the surface area, okay, so when you increase the surface area, of where the molecules are, or spread them out like I did. Okay. This increases the area where collisions can happen. This increase in collisions increases the rate of reaction. Okay. So that's another way. One of the things I always think of is my husband's up making another line for those freeze-dried Skittles everybody loves. They have to spread those Skittles out on a very thin sheet so they can get it faster and get more out of it, okay? So that when they put it through the big old freeze dryer, it happens quite quickly and they can keep up with demand, okay? Questions?